All right, yeah, thank you. Also, thanks to the organizer or the organizer who is here for inviting me and for this stimulating workshop. So I'll move from data that we already have to data that we'll hopefully have sometime in the future, which might help us to probe invisible physics at the future Muon Collider, and I'll talk about some opportunities that this might bring, but there are also a few challenges that people usually don't talk about too much. So my talk is mainly based on work in progress with Riccardo Mazzarotti, Ennio Salvioni, and Andrea Wulzer. And I'll also touch on a few things that I've done in the past. All right, so as you've probably heard, there's been a renewed interest in the Muon Colliders, and I say a renewed interest because it seems to come in waves. So this shows papers on Inspire Hab that are about Muon Colliders, and we're already in the third wave, more or less. There seemed to have been one in the 90s, then one which peaked around the Higgs discovery, and now, since we haven't seen much new physics at the LHC, it seems like the interest is spiking again. And the interesting thing is, in blue you see the HAB-PH papers, and usually during the previous waves, there was only a slight interest by theorists, but now it's actually still exponentially growing, the interest by theorists. And yeah, so the reason for that might be that now also the experimentalists are getting more serious, and there is a considerable R&D effort. There's even an international Muon Collider collaboration now, which had its first annual meeting this October. And I was there, and they're very enthusiastic about Muon Colliders, and they think they can do it. And also, there was an EU design study proposal which got accepted, so now they have money to actually do the whole R&D study. So this is definitely the right time to think about the physics potential of such a Muon Collider and what could maybe only be probed with such a collider. So what are the advantages of a Muon Collider compared to other colliders that have been proposed? And one of the main advantages is, of course, the energy reach. That's not only in comparison to other lepton colliders, but also in comparison to hadron colliders. So this plot here shows the energy of a proton-proton collider, which you would need to match 2-to-2 scattering cross-sections of a Muon Collider. So this is just a simple rescaling exercise. It's not very accurate, but it gives you a feeling, and it contains several different assumptions. So for example, these solid lines that beta equals 1 are electroweak interactions, and if you look here, then a 10 TeV Muon Collider could almost reach the same cross sections as at a 200 TeV proton-proton collider. So in terms of energies, you really gain a lot that you have an elementary particle instead of a composite object.
But this is just the cross section without background.
This is just the cross section. This is just showing that the cross sections grow a lot, more or less, because you have a large energy at your disposal, more or less. And also, of course, compared to other lepton colliders, since the muon is heavier than the electron, also there you gain a lot of energy. And in addition, since it's a lepton collider, you have a much cleaner environment as in hadron colliders. And also you have complete control of your initial state. So in principle, you could reconstruct the full kinematics of your event, which means that especially when you're thinking about invisible physics, you can also reconstruct your missing invariant mass, which is a huge help in searching for invisible physics. So in principle, a Muon Collider seems to be a perfect machine for studying invisible physics, such as dark matters or long-lived particles. So this brings me to my outline of the rest of my talk. In the first part, I will mainly talk about opportunities, where I'll focus on the scalar Higgs Portal to invisible physics. I'll mention the vanilla Higgs Portal scalar that already Jotam has mentioned. Then I'll talk about PNGB dark matter, and I'll also touch on invisible Higgs decays in a more model-independent manner. But this first part is completely idealized. So, and as it turns out, life is not always that easy, and you have to be more realistic when you talk about Muon Colliders, and there are a few limitations that people don't talk about that much, but that you have to take into account. And it turns out that actually accelerator and detector effects are very important when you make these studies. And in principle, you really have to do a more realistic benchmark scenario, which I'll do in the end in terms of the study of invisible Higgs decays and how good Muon Colliders will actually do. All right, let's start with the opportunities. So as I already said, I'll mainly focus on the Higgs Portal scalar, and I'll start with the simplest scenario that you could imagine, which is just a standard model singlet scalar phi coupled to the standard model Higgs through its marginal coupling, which is one of the three renormalizable proportions of BSM physics to the standard model. And since I'm mainly interested here on invisible physics, I'll assume that my scalar phi is either stable or long-lived at detector scales. And this is what many people call the nightmare scenario for BSM physics, because it's very hard to test. Because you always have to produce your scalar in pairs. It's completely invisible in your detector. And also, if it's heavier than half Higgs mass, then you always have to go through an off-shell Higgs, which also decreases the cross-section. But it is very well motivated, and it appears in very many BSM scenarios, which I will mention a few. The simplest is just a vanilla Higgs Portal scalar dark matter. So if the scalar is stable, and if you have a coupling that's of the order of 10⁻², then you can exactly reproduce the observed Lick abundance, and it's a good dark matter candidate. But also, such a coupling also appears in scenarios of neutral naturalness, where the scalar phi plays the role of a scalar top partner and is responsible for canceling the quadratic correction for the Higgs mass. And here you also have a very clear prediction of which effective coupling for this effective real scalar we have here you would expect, which is of the order of 3.4. So we can also use this as a good benchmark when we are comparing the mass reach at different colliders. Then such scalars can also induce a first order electric phase transition if we have large enough coupling. This really requires coupling of order 1 or larger. So the last two cases are really perfect for testing at colliders because we have large couplings. But for the scalar dark matter, because couplings are rather small, this is pretty hard to test at a collider. But for dark matter, you can also, there's also another way for testing it directly, which is just in direct detection experiments. And the vanilla Higgs Portal model is already almost completely excluded by direct detection. So it's already sensitive to portal couplings of the order of 0.007, which is much smaller than you would need to get the right Lick abundance. And so you in principle exclude everything up to a few TeV. There's only a small region that's still allowed around the Higgs resonance, but everything else is almost completely excluded. But you can still have Higgs Portal scalar dark matter in expanded theory. So you can, for example, add extra scalars, or you can talk about non-standard cosmology, but I'll not touch on this anymore. Because there's also a different way in which we can have Higgs Portal dark matter. Because here you see the reason why it is excluded by direct detection is that you have the same coupling, a marginal coupling, which has the same strength in direct detection experiments as in annihilation, which set the Lick abundance. The principle you can avoid this problem if you have a energy-dependent coupling, which brings me to the derivative Higgs Portal. So you have, instead of a marginal coupling, which couples the Higgs to the dark matter candidate, here you have a derivative coupling. And if this scalar phi is stable, then this is a scenario that's usually called pseudodynamic Goldstone dark matter. I'll talk more about the motivation in a second, but let's first assume that this is actually the leading coupling of the dark matter candidate to the standard model. In this case, this derivative coupling induces an energy-dependent coupling of the dark matter to the standard model. So this means at annihilation scales, it is still strong enough to set the right Lick abundance. So in this case, we get the right Lick abundance for electric scale masses, so around 200 to a few TeV. 4 suppression scales of the operator, which are around 1 TeV to a few TeV. But at the same time, at direct detection experiments, where you want to measure the recoil of nuclei after they scatter with like matter particles, you're sensitive to the momentum exchange, to T. And since this is very small at direct detection experiments, the whole cross-section is strongly suppressed, and PNGB dark matter is practically invisible in direct detection experiments. But this also tells you that the best way to test this scenario is to go at the highest energy possible, which would mean colliders. So where does PNGB dark matter appear? So it naturally arises, for example, in composite Higgs models, that is in non-minimal composite Higgs models. So one minimal example in that sense would be if you have a strong sector with simply breaking SO6 to SO5. In this case, you would not only get the Higgs doublet as a Goldstone boson, but also a real singlet scalar phi, which in this case would be the dark matter candidate. And in this case, you would get this derivative coupling between the Higgs and this new scalar through the nonlinear sigma model kinetic term. There you get exactly this coupling that I showed before. But also the point here is that since both the dark matter and the Higgs arise as PNGBs of the same single breaking structure, they also come with the same decay constant. So the size of this derivative portal is expected to be of the similar size as correction to the Higgs coupling. So in principle, you could also look for this scenario by measuring Higgs couplings. But what is pretty nice about this scenario is that also the dark matter stability can come from the new strong sector. For example, if you have single breaking that's SO7 to SO6, and instead of this real scalar, you have a complex scalar, which is charged on an unbroken U1 of your strong sector. But here you always have to, you need to have the Goldstone simply breaking under control, because you want a mass for the dark matter, but if you also induce a marginal coupling from the dark matter to the Higgs, which is too large, then you're excluded by direct detection. So this marginal coupling has to be suppressed. And there are some easy ways to do it. So if you're interested, I can tell you more about this later. It's not too hard to model build this scenario. But you don't need a composite Higgs models to get PNGB dark matter. You can also only have the dark matter as a PNGB. You don't need your Higgs to be a PNGB. For example, if you just start with this simple Lagrangian where you have an additional complex scalar S, which is charged in a U1, which is only softly broken by, for example, this mass term here. And once the U1 is spontaneously broken, you can integrate out the radial mode of your field, and you get exactly this derivative Higgs portal. But what is interesting in this model is that the corrections to the Higgs couplings, which you get after integrating out this radial mode, scale differently than the Wilson coefficient for the derivative Higgs portal. So in this case, you could parametrically suppress the corrections to the Higgs couplings, so that instead of the same scaling which you get in composite Higgs models, you might not be able to test the scenario by just measuring the Higgs couplings. So here, a direct search for this dark matter candidate would be even more important. All right, so now after this motivation, how can we actually search for this? So I will focus on a Muon collider, but in principle, this also applies to any lepton collider. You always have to produce it through the Higgs. And the main production channel for the Higgs is vector boson fusion for center of mass energies larger than 1 TeV. And the thing is, you have to produce it through Z-Z fusion, because WW fusion would give you a completely invisible final state, where instead of muons, you would not have neutrinos here. You would not see it at all. So you always have to go through Z-Z fusion. And what's also interesting here is that you have a very different scaling of the production cross sections for the derivative and the marginal portal. So not very surprisingly, since it's through an effective coupling, it grows with energy, but it's approximately independent of the dark matter mass. So you can more or less produce it almost up to the production threshold. While for the marginal coupling, the cross-section falls with the dark matter mass. And the main background here is, of course, just muons with neutrinos. The kinematic variables that you can use are, for example, the time muon invariant mass and its VDF channel. You can also use that the muons are expected to be very forward. And of course, missing invariant mass is a very important kinematic variable. That's because if you have a dark matter that's below half Higgs mass, then it's in principle just looking for invisible decays of the Higgs, and you have just a peak at the Higgs mass. So it's pretty useful to suppress the background. But if it's heavier than half the Higgs mass, then for the marginal portal, you mainly produce it on shell. So you have a peak of your missing invariant mass at twice the dark matter mass. But interestingly, for the derivative portal, the coupling grows with additional energy that's going through the coupling, which in this case would be the missing invariant mass. So also the spectrum of the missing invariant mass grows at larger values. So this is also very useful to suppress the background. Now about the result for this simple analysis. So this is for the marginal Higgs portal, where I show the projected constraints you would get on the portal coupling as a function of the mass. And as you can see, the lepton colliders, no matter if it's a muon collider or a click or RLC, they usually perform much better than hadron colliders. So click at 3 TeV would more or less be exactly as strong as FCC 100, which is mainly due to the missing invariant mass that we have access to. And if you compare the reach in the masses at this measureless-inspired coupling value, then you see that, yeah, if you compare click with FCC 100, it's almost the same, but a muon collider at 6 TeV would massively outperform FCC 100 here. And if you look at the regions of parameter space that are interesting for first-order electric phase transition, which are shown in shaded gray and blue here, and you see that also in order to test more or less the full range, a muon collider would be very important. And even FCC 100 could not probe the full region of parameter space. Now for derivative Higgs portal, in this case, here I show the exclusions for the suppression scale as a function of the mass. And first thing that you notice here, the bounds are almost flat, which is exactly what I told you before. The cross section is almost invariant under the mass. So it's very flat until you reach the production threshold. But also here, lepton colliders almost always outperform the hadron colliders. And the target here that you have to look at is the terminal Higgs density contour, and that can really only be probed in the interesting values of suppression scales between 1 and 2 TeV by a muon collider. So there's really nothing else that can probe the interesting region for PNGB dark matter. All right, so this was the first part, which just had a very idealized view on muon colliders and anything else. So are there any questions up to now before I turn to the challenges?
How did it compare with Higgs couplings, this last case, you know?
Higgs couplings?
You said in one case they are correlated, yes?
Yeah, so in composite Higgs models, they are of course correlated, that's true. So I don't know the numbers on top of my head, but I would say, yeah, it's Higgs coupling measurements are probably at least as strong as the direct searches here. But like I said, it doesn't have to be correlated. So in these simple models where you just add a complex scalar and get a PNGB from there, it can parametrically suppress, so it doesn't have to be correlated. Any other questions? All right, then let's go on to the challenges. So there's one big caveat in everything that I talked about so far. The coverage of forward muons is really crucial because it's a VDF process, so the forward muons are very, the final state muons are very forward, which you can also see here in this distribution, which shows the rapidity distribution for both the background and the signal. And while the background is almost flat over the whole range, both the derivative and marginal Higgs portal are peaked at around an eta of 5, so maybe half a degree. And the problem is that in current designs, detector coverage only goes up to an eta of 2.4. So this would mean you lose all of your signal. There's really nothing that you could do. And just as a comparison, in the previous studies, we assumed a coverage of eta goes up to 6. So when we did that work, then yeah.
Why is the 2.4? What is the limitation in data coverage of the?
That's my next slide. Right. Yeah, so back then when we did this previous study, we actually didn't know about this. That's why we assumed an optimistic coverage of up to 6. But the problem is, as it turns out, the large beam-induced background that you have. So muons are unstable, so they will also decay in your beam. And then you have a lot of electrons and neutrinos that are very boosted along your beam. So the forward region is very busy and you have to shield your detector to protect it. So what they actually do is they shield the forward region with tungsten nodules. And yeah, so this is where it comes from. So it's 2.44 because that corresponds to exactly 10 degrees. I think they were more thinking about degrees instead of.
Muons are very boosted. So what is the opening angle of the decay product of the muon? It's much less than 10 degrees, no? It's like ME divided the boost by the energy of it.
Yeah, but also I have to say that the current studies are not for like a 10 TeV collider, but for much lower energies, for 1.5 or 3 TeV. Yeah, but right, so they're very boosted. But also, even if you have this nodule that you need to shield your detector, in principle, you could still have a forward detector because the muon goes through the shield and then you can detect it further away. And that's more or less what we want to make a physics case for. And there it turns out that detector and accelerator effects become very important because if your muons go through this nodule and you detect it later on, then you don't expect to have a very good energy resolution, and also many more effects become important if you look at very forward objects. So to make really the case for muon detector, you need a more realistic study. And for this, we use as a benchmark invisible Higgs decays. And just as a benchmark, at FCCH8, the projection is that you can test the branching ratio of Higgs invisible up to 2.5 times 10 to the minus 4. Now the question is, at a muon collider, could you do better than that? And how good could you do as a function of the detector coverage? Because as already mentioned earlier, okay, first, so again, we consider in this case benchmark set of mass energy of 10 TeV. And again, the main production channel is through Z fusion, same as before, and also the same background as before. But also, as I already mentioned earlier, in contrast to hadron colliders, at a muon collider, you really have the missing invariant mass, which is really essential to spread the background. We can really cut out a small region around the Higgs peak to suppress a lot of the background. So you might think that a muon collider should be able to do much better than the FCCH8. So that's the first step. We just did a simple analysis at Parton level, again, cutting on the same variables and also cutting out a small window around the Higgs peak in the missing invariant mass. And we just tried to see how good a bound we could get as a function on the detector coverage. And as you see, if you have the detector coverage of 10 degrees or 2.44 in eta, then the bound that you would get is 2.2 times 10 to the minus 1, which is much worse than CMS and Atlas right now. But every degree that you increase the detector coverage, the branching ratio, the sensitivity to the branching ratio grows exponentially. So every degree helps a lot. And in the end, if you have unlimited detector coverage, then you have a total value of 5 times 10 to the minus 5, which is almost an order of magnitude better than the FCCHH. But again, this is still idealized conditions, because here now also you become sensitive to irreducible imperfections of your missing event mass reconstruction. Because what we assume is that we can completely reconstruct our missing form momentum, and for this you need to have a perfect knowledge of the initial state. So what we usually assume is that you have a head-on collision with both muons having the same energy, but this is of course not true. You always have a small beam energy spread, and this will turn out to be important. Also, you have a beam angular spread. You're not always in a head-on collision. You often also have small spread in the angles of the muon. Then also, as already said, there's definitely an uncertainty in the energy measurement. You cannot assume to have a perfect resolution, especially for forward muons. And then there could be anything else, some particles that you lose, especially if you have these nozzles in the forward region, they can just absorb a photon that you then completely lose. So this is important in two aspects. First, because of these imperfections, your missing form momentum could be space-like. So then you have like an imaginary missing event mass. So what you do with that? So we thought about two different definitions. Either you just take the absolute value, or you all collect them at 0 and just take the real part. Then also you have many high-rate processes which become important, like Babar scattering. If you have an imperfect measurement of the energies, then this could look like it has some missing event mass. And the same, if you radiate a photon which gets lost, then also this might look like your signal. The first thing that we looked at was beam energy spread. So we assume that both muons don't have exactly the same energy. And if this is true, then your detection frame is not your center of mass frame. There's a longitudinal boost which relates the two of them. And the expected beam energy spread that you have at a muon collider is about 1 per mil. While this sounds small, if your muons are very forward, they're very, very energetic in the forward direction, and you have a boost, then this 1 per mil boosted is a large effect, and your missing very mass distribution gets very smeared. So here we have the same distribution with the signal in red and the background in blue. And now also, you barely see it in green, and in purple, you have the Babar scattering and the one with an additional photon which gets lost. And if you have a perfect reconstruction of all your momenta, then these still have missing event mass 0 because your photon is massless, and it would not overlap with the signal at all. But if you have beam energy spread, it spreads out a lot. So the spread of the Higgs peak is not that important. What is much worse is the background with an additional photon that gets lost, which now completely swarms the Higgs peak. So why is that? Why is there such a big effect on that? As it turns out, you can do a bit of an analytic estimate using the kinematics. And it turns out that the width of the missing invariant mass peak of the photon distribution is sensitive to the longitudinal part of the photon form momentum. But this also means that the ones that are problematic for us are photons that are very energetic in the longitudinal direction. So they are hard collinear emission, which is actually pretty good because soft would be much harder to differentiate. Because if it's hard collinear, then the energy has to come from somewhere. This means that one of the muons in the final state will be less energetic. And then you can, for example, cut on the energies of the final state muons to remove this background. which you can see, for example, here. So there's a clear correlation in the minimum of the energies of the muons and the missing event mass for the background in green, whereas the signal is up here. So we can easily use a cut in the minimum of the energies to get rid of large part of the background. Yeah, so just comment on the photon background. So the way we generated it so far is not very sophisticated. It's just at fixed order, and we assume that every photon that's in the forward region gets lost. And so far, we have not included any radiation from the signal. So improving the simulation is still a work in progress. So in the beam angular spread, so the average angular spread at the Muon Collider is expected to be 0.6 millirad. And in this case, the boost is not along the longitudinal direction, but the transverse direction. But since the muons are very forward, the boost in the transverse direction doesn't change that much. So it seems to have a very small effect on the analysis. Still near distribution, but only by a little. So now nothing really overlaps with the signal region. Now, the last effect that we looked at was the energy measurement uncertainty. This is the distribution that we start from with a beam energy spread. And if you assume that you only have a very mild uncertainty on the energy measurement of 0.1%, this doesn't change much. But already at 1%, your Higgs peak is almost completely gone. And even the Rabat scattering, which has a huge rate, now almost completely overlaps with the signal. So it seems almost hopeless in that case. But it turns out that the Rabat scattering background can be efficiently suppressed with a cut on the missing transverse energy, because it doesn't have much missing energy in the transverse direction. Now, if we combine everything, that's where we started from. In an ideal world, you could have this sensitivity on the branching ratio of Higgs into invisible. And if you include 1 per mil beam energy spread, still pretty good. But once you have some uncertainty in the energy measurement, you really quickly lose sensitivity. And for 1% energy uncertainty, you jump up quite a lot. If you compare this to the benchmark, to our FCC H8 projection, it's still competitive, but only if you're able to measure very forward muons up to an eta of around 6. Right, so our next steps are to improve the simulation, also include photon radiation of the signal, and also include further detector or accelerator effects, such as a displacement of the interaction point, and also apply to different scenarios. And if you have any suggestions or comments that what we should also look at, then I'm happy to hear it. So my conclusion now is that a high energy Muon Collider can be the perfect machine for studying invisible physics, but only if you have a forward muon detector, because only then you can really reconstruct the missing invariant mass and use it for your study. And as it turns out, in this case, all detector and accelerator effects are non-negligible for forward muons. All right, thank you.
Thank you, Max. Are there any questions?
Yeah. What are the typical energies of your final state muons?
Final state muons. I think you can see pretty good here. So this is the minimum of the energies of the mu plus and mu minus. And you see for the signal, they're very energetic. So they are close to 5 TeV in a 10 TeV Muon Collider.
Okay, so in your detector, they're gonna branch travel photons a lot. Well, maybe not a lot, but it's a question, not entirely a statement.
Yeah, so we really haven't thought much about the detector yet. So we have talked to a few experimentalists, and they say it's very difficult to get a good energy measurement. So their most optimistic estimate was actually that they might be able to do is around 10% uncertainty in the measurement. But that was until now the most optimistic scenario. Yeah.
You are going to get the muons from?
Excuse me?
How are you going to generate the muons for the Muon Collider?
Oh, I am not doing that at all. I hope the experimentalists will be able to do that for me.
Okay.
Yeah, but I think what they were mainly talking about at this conference was doing it through pion decays. So we're using pions and then.
And do you know at what level is the FCC estimate? I mean, because you did a lot of good work, but I'm not sure that all the estimates for these future colliders take into account these effects at the same level of detail.
Yeah, I'm not completely sure about that. So this was the estimate that I could found in this report. I don't remember what level of rigor they did it.
I'm just trying to say that maybe also their bound is gonna get worse.
That might be the case, yeah.
Just a curiosity.
Yeah.
Really stupid question, but since the numbers are such, so aren't there any channels where you should worry about some neutrino nuisance? I mean, the flux of neutrinos must be huge, right?
Mm-hmm.
Of energetic neutrinos and PEV. So isn't this for some channels or measurements a concern? You cannot shield them, right?
Yeah. Yeah, I don't really know, but it might very well be, yeah.
They are forward, right?
Yeah, and just like electrons, you have the same problem as electrons, just that they go through.
Actually, I think that initially, like in the 80s, maybe the Muon Collider was, let's say, put on the bench because they thought that the neutrino flux would kill people.
Well, not kill people, but generate events.
That's the size we're talking about.
Yeah.
But now I forgot. Why do they think that in these new designs it's okay?
So they did a few radiation simulations, and I don't know why exactly, but they claim it's okay. It's not at a dangerous level, and also the detector can survive long enough.
I'm sure there will be volunteers to be the first person killed by neutrinos, but just like volunteers to go on Mars one way.
Okay, so I don't see more questions, so let's thank Max again.